So we're going to look today at balancing equations, and this might be revision for some of us, but it's a really important skill in chemistry. So we're going to do this by looking at some examples first of all and thinking about what they mean. So my first example is going to be the reaction between magnesium and hydrochloric acid, which makes magnesium chloride and hydrogen gas. So before we start to think about actually how we're going to balance this, we need to recognize a few things. We need to know that everything on the left-hand side of the arrow are the reactants, and everything on the right-hand side of the arrow are the products. And the total amount of the atoms that are present in the reactants must equal the total atoms that are in the products. And that's because of the conservation of mass in chemical reactions. So, whenever we're thinking about balancing equation, it's always worth just drawing a little line, a squiggly line under the arrow to show that everything we do here has got to match everything that we do here. So let's think about what we've actually got here. So this represents a magnesium atom. So I'm just going to draw that as magnesium with a circle. And this represents a hydrochloric acid molecule, which is made up of a hydrogen atom bonded to a chlorine atom. And that's really important because hydrochloric acid comes as hydrogen bonded to chlorine. When I'm balancing my equation, I can't change anything about that. The hydrogen atom will always be bonded to the chlorine atom in a hydrochloric acid molecule. Sometimes it's worth also drawing boxes around the individual components in our equation because it might help us when we're coming to balance it. So let's have a look at this side. Well, magnesium chloride is made up of a magnesium ion. Don't worry about what the difference between an atom and an ion for now, just being clear, and two chloride ions, which I'm going to draw as magnesium stuck to a chloride ion there and a chloride ion there. And it's also made of a hydrogen molecule, which I'm going to draw as two hydrogen atoms bonded together. And again, I'm just going to draw a box around these to show that I am aware that these are individual components in the chemical reaction and that I can't change anything about them. I can't change the fact that magnesium is bonded to two chloride ions. It has to be MgCl2. I can't change the fact that hydrogen exists as two hydrogen atoms bonded together. So let's have a look at the left-hand side. On the left-hand side, we can see that there's one magnesium, there's one hydrogen, and there is one chlorine there like that. Now, if we look over the other side, and I'll do it in the same order as here, there's one magnesium here, but I can see that there are in fact two chlorines, and there are two hydrogens. So having a look through these, we can see actually the magnesium is balanced, but the hydrogens and the chlorine aren't. And the reason is we've got two hydrogens on the right-hand side, only one on the left. Two chlorines, only one here. So how do we go about balancing this? Now remember that we can't simply stick another hydrogen on here and another chlorine on here because that would change the nature of hydrogen chloride. So what I can do is add to this side another molecule of hydrogen chloride, of hydrochloric acid. So I've added, because I can see that as a H bonded to a Cl, I can add a whole nother unit of that. What that does is now means there's two hydrogens here, 1, 2, and there are two chlorines here, 1, 2. I can also then have a look back at the equation and go, I've got one of these and another one of these, so I can put a big 2 in front of the HCl there, like that. And now that's balanced. Let's have a look at our second example. So our second example is the reaction between potassium and sulfuric acid. And that produces potassium sulfate and hydrogen. So let's have a look at this one. First thing again, draw that squiggly line down like that. This means a K. This one's a bit complicated actually, so it's going to take me a little while to draw it out, but that's a sulfur bonded to 4 oxygens and a hydrogen bonded to 2 of the oxygens. You don't need to worry about why I've drawn it this particular way. That is actually the way that we would think about drawing it, but it really doesn't matter as long as we recognize that all of these atoms are stuck together in some particular way. Let's go over the other side. This one's going to be a little bit different. So I'm just going to draw this like this. The way that the potassiums are stuck to this is in a slightly different way to this one. Again, it doesn't matter as long as we realize that these are all bonded together, stuck together in some particular way. And then my H2 unit here. So I can't change anything about that. I can't remove one of these potassiums. I can't add more because that's the formula for it. So I'm showing that by just putting boxes around each component in the chemical reaction. So let's do that thing that we did last time, which is to work out the number of each type of atom on either side of the reaction. Potassium there, I've got 2 hydrogens, H2, 1 sulfur, and 4 oxygens. Let's go and do the same thing over here. This time we've got 2 potassiums. So we can see actually that that's already see that isn't balanced. There's 2 hydrogens here, 1 sulfur, and 4 oxygens. So in fact, these 3 are balanced. So all I need to do over here is add another potassium, another K. That then means it's balanced. And I do that by putting a big 2 in front of the potassium. So those ones have been relatively straightforward. We've only really had to change one thing in the equation. Let's have a look at one where it's not quite so straightforward. And that's the reaction between sodium, which has the symbol Na, and a chlorine molecule, which is Cl2, and that produces sodium chloride, NaCl. Squiggly line down the middle there like that. Draw this out as a diagram. NaCl bonded to Cl. Na and Cl here like that. So let's do the process of working out how many of each type of atom we've got. 1 times Na, 2 times Cl. 1 Na there, 2 Cls here. On this side, just 1 of each. So this is balanced, but this is unbalanced. Now this is an example of one where we're going to make a change in order to start balancing it, but it's actually going to, in the process of doing that, unbalance something that we thought we'd already sorted out. So I've got 2 chlorines here and only 1 here. Now remember that I can't change anything about this. So what I cannot do is put a little 2 after this. Okay, that would be incorrect to do. The reason being is that is the accepted formula for sodium chloride. That's why it's quite helpful sometimes to put these in a box, because it means that I can't add any little numbers in here. When I'm balancing, the only thing I can do is put big numbers in front of the components. So let's put a big number 2 in front of here. What that does is means that there are 2 each of these. So I'm going to add another NaCl. So that has now made this 2 chlorines. So this is balanced. But in the process of doing that, it has unbalanced the sodiums. So now I need to go back to the other side and add another Na and put a 2 in front of this, which means that is now 2. And I have indeed balanced the sodiums. So this was an example of when I started to balance one thing, so I started to balance the chlorines, it unbalanced the sodiums. And that's what often happens with balancing equations. We do one thing, but then it means we have to go back and change something else. So let's have a look at probably our most complicated example, which is going to be a reaction between sodium and water. Just out of interest, both of the reactions that you've just seen, the one there and the one here, are ones that you are going to need to remember. But I'm going to write those down at the end of the video for you as well. So let's go through our process. We've got a sodium here, and we've got water, HOH. Boxes around them. I can't now change anything about that other than to put big numbers in front of them. I've got a sodium, an oxygen, and a hydrogen, sodium hydroxide, and a H2 molecule. So let's go through our process. 1 Na, there, 2 hydrogens, 1 oxygen. Over here, 1 Na, 1, 2, 3 hydrogens, and 1 O. So let's start by looking at the thing that is unbalanced, and that is the hydrogens. This is going to be a slightly more difficult one to balance because obviously we've got a 2-to-3 ratio. So the way I'm going to start trying to do that is to recognize that I'm going to have to get this up to 4 probably, so that I can balance by even numbers. So I'm going to put a whole other NaOH in here. So that means putting a 2 in front of here. What that has done is means I've now got 2 NAs because everything inside this box has been multiplied by the big number here. I've now got 1, 2, 3, 4 hydrogens. Hasn't really helped, but I've got these to numbers that are divisible by each other. And I've got 2 oxygens, like that. So having done that, I'm going to need to go back over to this side. Well, the first thing that is unbalanced is my NAs, so I need another Na. Put a 2 in front of that. That is now balanced the NAs. 4 and 2, 2 and 1. So if we look at that H2O there, I can add another H2O, putting a 2 in front of that. That then means 4, and that means 2. So this one is an example of a balancing equation where it's a bit of a trial and error process. Do something, see if it works, go back. But the key thing that I recognized, and it was the problem that we had this 2-to-3 ratio with the hydrogens. That meant that they aren't going to go into each other. So I'm likely to have to get this up to 4 because 2 will obviously go into 4, or I could get it up to 6 because 2 will go into 6, or I could have got this up to 6 because 3 will go into 6. So just recognizing that 2 and 3 often means that it's going to be a slightly tricky one to balance. Okay, thank you very much.